Okay, guys, I'm going to go over the notes to section 13.1 that I have posted. And just to remind everybody, these are taken from the online version of the textbooks, since most of you probably did not bring home your actual textbook. So please make sure you're referring to the online version, the PDF version that I posted several days ago. And I just also want to stress that these last two chapters we're covering have been exempt by the AP for the AP exam, but we're still covering the information. So the topic we're going to is chapter 13, periodic motion, or in other words, oscillations. So section 13.1 is just a brief introduction to this stuff. First of all, describing oscillations. Objects that oscillate which we will study are springs, pendulums, and things of that nature. And these all have what's considered an equilibrium position. That would be a position where they would come to rest. The term displacement, as always, represents how far and in what direction an object is from equilibrium. And the restoring force we talked about before when we did Hooke's law, and that may come back here at times, is considered the force necessary to restore an object back to equilibrium. If you remember, Hooke's law was F equals negative kx. The negative was there for the fact that it was restoring back to equilibrium. Now, some important terminology you'll use with this stuff. You'll probably notice that a lot of these terms are related to things with waves, because waves basically are a type of periodic motion as well. So typically moving forward, a topic after this one in the general physics curriculum might be jumping right into waves, since it's closely related. If time permits, at the end of this year, we may do some things with waves. Anyways, some important terms you should know are amplitude, and that just is considered the maximum magnitude of displacement from equilibrium. Period, the time it takes for one complete cycle back and forth. Frequency, the number of cycles per unit of time. The most common unit for frequency is hertz, abbreviated Hz, but 1 hertz is the equivalent of 1 cycle per second, 1 full cycle per second. Frequency and period are related to each other. They are simple inverses of one another. In other words, period big T equals 1 over frequency, and frequency equals 1 over period. Another thing that will be used that we are already familiar with is angular frequency, omega. And angular frequency is just simply 2 pi times regular frequency. And there's some of the formulas which I already relayed, simple, basically conversion formulas. So real simple example, 13.1 in your books, just converting some of these things. So we're given here a frequency of 6.7 times 10 to the 6 hertz. And we're asked for two basic things. What is the time period? And what is the angular frequency omega? Now, the math is very simple here, but what's most important is what we realize what we're solving for, what it represents conceptually. So remember, the given frequency right here, this value in hertz, this represents, let's think like a typical back and forth swinging pendulum like we've used for like energy when discussing transfers of energy. So if this was the frequency of a back and forth swinging object, I know it's a little crazy high for something like that, but just for ease of explanation, This represents how many full cycles occur per second of something oscillating back and forth. So anything going back and forth that has a 6.7 times 10 to the 6 hertz frequency, what that really means is that in 1 second, it completes 6.7 times 10 to the 6 full oscillations. Now, for a mechanical device, that is a ridiculously high number, but when dealing with waves, that's definitely in the ballpark of high frequencies, which naturally occur, especially with an electromagnetic waves. All right, so when we want the time period, as I said earlier, time period and frequency, as long as the frequency is in hertz, are simple inverses of one another. So we do that. Take the inverse of the frequency, and again, as long as the frequency is in hertz, that will give us the time period in seconds. And this is a ridiculously small number for time period since there's so many cycles occurring per second. And this just represents big T, the time period, the amount of time it takes for one full cycle. So one full cycle of oscillation for this system is 1.5 times 10 to the negative 7th. We've also recently, during rotation, studied angular frequency. We can imagine cycles around the unit circle. So a full cycle of something swinging back and forth one complete time over and back, going through a full cycle, could be thought of going around the unit circle, which is why we could put this stuff as an angular frequency, as discussed before. And the angular frequency equation is simply omega equals 2 pi times the regular frequency we put here. So the angular frequency is going to be 4.2 times 10 to the 7th radians per second. Pretty easy stuff, but it's more important to understand what you're doing right now. Below I have a what looks like a cosine function to represent this visually. We will be doing more and more of this through this chapter. So some of the terminology on a position time graph. Right? The vertical axis represents a position X, and the horizontal axis represents over time T. So as we discussed earlier, the amplitude is the max displacement away from equilibrium. So if we graph the position versus time of any object that is oscillating, we will have a max amplitude and a min amplitude. And the t-axis represents the equilibrium position, because right here, position equals 0. So there's always a positive amplitude, max positive amplitude, and max negative amplitude, because there's two directions you could go away from equilibrium with oscillating objects. And the time period is the time it takes for one full cycle. Now, one full cycle would be like from max amplitude to the next max amplitude, not max to min. Max amplitude to the min amplitude represents only 1/2 of the time period. So that's just a visual that you could get from understanding the graphing nature of some of this. And that's really all there is right now for section 13.1. It's just getting our feet wet with some of these basic calculations and terminology. So at this point, you may review these notes again on your own. Look back on the posting on Google Classroom for the assignment and practice problems on this information.